This is a production of Cornell University.
Good morning, everyone. So I direct Cornell's Controlled Environment Agriculture Group, which is growing plants in greenhouses and indoors. So I was curious how many of you work with growing cannabis products in greenhouses or indoors in some capacity, by show of hands. Okay, good. So my talk today will be most relevant to you. If you're growing in the field and you work with transplants that you receive, this is also going to be relevant. So I was asked to speak specifically on substrate testing for soilless hemp. And so that root zone where hemp is grown, either propagating plants or growing the plants through till flowering, is very important. And you can really affect the plant health and productivity through that root zone. So instead of growing in soil, when we're growing in containers, we say that we're growing in soilless media or soilless potting mixes. And the goal of that media is the same as it is in the soil, which is to store and supply water, nutrients, and oxygen to the plant. And that oxygen component is actually really important. Roots need oxygen to respire, just like we need oxygen to breathe. And hemp roots are very sensitive to root diseases if they don't have sufficient oxygen. That soilless mix, that media also anchors the plant into the container so they don't flop over. And then I'm going to talk about the important physical and chemical properties that you can have tested of your potting mixes. So just as an introduction, the different soilless media that we have available, we often split those into two groups. One are the organic components, and what I mean by organic in this case is carbon-based. So they're typically plant or animal residues. And coconut coir is very common, the shredded husk of coconut that can be compressed and easy to ship. Peat, decomposed sphagnum peat moss, composted bark and wood, rice hulls, biochar, and compost. So those, because they're carbon-based materials, they have fairly good nutrient holding capacity as well, or cation exchange capacity is what we talk about. And then we also have inert components that are not carbon-based. So those would be like this picture on the bottom right, which is stone wool or rock wool, is a spun insulation material. It has very good physical properties. It's good at holding on to water and allowing airspace, but it doesn't have an additional nutrient holding capacity. So when we're growing plants in this type of substrate, we have to supply nutrients every time that we're watering. Perlite and vermiculite are other examples of that, as well as lightweight expanded clay aggregate. So it's important to know the materials that you're using. You can talk with the manufacturer of them to see if they should do their own in-house testing for these physical and chemical properties that I'm about to talk to. That would be a sign of a reputable supplier. If they can't provide you with a nutritional test or information on the physical properties, you can also do some of the testing yourself, which I'll talk about, and other components you can send to a lab. So when we're talking about the physical properties, this is the balance of the water holding and air porosity. And so when we fill a container with a mix, we have the substrate itself, or the particles itself, and then we have space that's not taken up by those particles. And when we water a container to container capacity, that is watering a container fully with water and allowing it to drip drain, then of those total pore spaces, they're going to be divided into some of those spaces are still holding air. So that's called the air-filled porosity, and that's a percent by volume. And then we have water holding capacity. So those are the pore spaces that are filled by water. And so the right soilless media is going to have a balance between the moisture holding and the air porosity. And one of the ways that we can think about that is that water holding capacity and aeration balance and the height of the water table in the pot is really only affected by that particle size, where a smaller particle size is going to be like that container on the right that holds more water and less air. And if you have a larger particle size, you're going to hold more air and less water. And often you will see that potting mixes are formulated to contain multiple components. So we might have like peat as well as perlite and vermiculite because together they give us the physical properties that we need. Their combined particle size balances moisture and air. So the metric that we're really looking for here is that the total porosity should be equal to 50% by volume, and then the water holding capacity within that should be at least 40%. And then that means the air porosity should be at least 10%, because air porosity plus water holding equals total porosity. And where that 10% comes from is in the traditional greenhouse world, not necessarily the cannabis world, but they found below that 10%, there's poorer root growth and not enough oxygen to support a really good, robust root system. And where that 40% comes from is the lower that number is, the more frequently you need to irrigate your container. So if you were overhead watering, maybe you would have to water 3 times a day if you had really poor water holding capacity. And just an example of physical properties of some of the different substrate components that we use. Often peat by itself, peat comes in different layers depending on how long it's been degrading. And some of the kind of virgin peat that's toward the top that has been degraded for a less period of time actually could serve as a potting mix by itself. It has sufficient water holding and it has at least 10% air-filled porosity. More often than not, we have to add perlite or vermiculite to peat to improve its air-filled porosity. And then coconut coir is often used as a material by itself. Coconut coir also varies in its how well degraded it is or how fibrous it is. But you can find many coconut coirs that by themselves have sufficient air porosity, have very good water holding capacity. And interesting in this case, it's 95% total porosity. So that means when you buy that coconut coir, you're only getting 5% by volume is actually that fiber that you're paying money for. And the rest is airspace or water space. So I'm going to move on to chemical properties. So pH really affects the availability of nutrients in the root zone. And it's been said that about half of the nutrient disorders that we have are related to an improper pH and not due to lack of the nutrient itself. So this graph shows us availability of the different nutrients that are important to the plant as the pH increases from 4 to 8. And so with some of the nutrients like nitrogen and potassium, we're pretty lucky. They're actually widely available in the root zone across that broad pH range. And then we have several nutrients like phosphorus, and then all of the micronutrients, iron, manganese, boron, and so on. We're really above a pH of about 6.5 in a soilless media. Those get locked up and are not available for roots to take up. One thing about soilless media is they do have less buffering capacity than our traditional field soils. So with the field soil, we could get away with a higher pH, but in a soilless potting mix, we're really looking for this more narrow range. On the low end of the spectrum, if we move below a pH of about 5.5, we have issues with calcium and magnesium availability. And at low pH, we can also get too high of phosphorus solubility. That means our phosphorus can leach out of the container too readily. So really the optimal pH we're looking for hemp or cannabis in general is 5.5 to 6.5. And for monitoring, we recommend targeting 5.8 to 6.2. And then if you're, say, tracking pH every week, which I'll talk about, once you track out of that range, you would start taking action so that you have some time before you get out of that 5.5, 6.5 range. So there's several factors that affect root zone pH, and one is your water source itself. Many of our well water sources in New York are high in their alkalinity. There's limestone deposits under the earth. And so the carbonates and bicarbonates in that water are like liquid limestone. They essentially increase the pH of our root zone over time. And so we often see that in Western New York and upstate New York, where our well water is high in alkalinity and our pH is creeping up over time. The fertilizers that we use also affect the pH. So a more ammonium or urea-based fertilizer is going to decrease the pH. and a nitrate-based fertilizer increases the pH. So that's actually a tool that we have to use to adjust pH, is adjusting our fertilizer. And then we can also use acids to decrease pH. So I mentioned problems with pH being too low, which are especially our deficiency of calcium and magnesium, leaching of phosphorus. And if we get very low, sometimes less than like 4.5 or 5, iron and manganese and zinc and copper become very available to the roots to take up. And we can, in some cases, see toxicity of those micronutrients. And then when pH is too high, which tends to be a more common problem with the waters that we have in upstate New York, we get deficiency of those micronutrients, iron, manganese, and so on. And so this is a photo of iron deficiency, which affects the upper leaves, the youngest leaves on the plant. And we get yellowing of those upper leaves, starting at the base where they attach to the stem. And then in particular, the veins themselves will stay green, but the interveinal region will be lighter yellow. The other major chemical property that I want to talk about is electrical conductivity, or EC, and we use this as an overall measure of fertility. What it does is it allows us to use a handheld sensor to get a measure of the overall salts that are dissolved in water, and it takes advantage of the property of water that pure water doesn't conduct electricity, but water with dissolved ions in it can conduct more electricity. Low EC indicates low overall salts or low overall fertility, and then a high EC indicates high fertility or overall high salts. With hemp, and I'll talk about testing methods, but with the pour-through testing method, we're looking for an EC reading of about 1 to 2.5, depending on the crop stage. And this is a photo of nitrogen deficiency, which we would get often with overall low fertility or low EC, which is lower leaf yellowing and small plant size. So we're still in our early days of knowing exact fertilizer recommendations for cannabis. That's actually, or hemp, that's actually one of the things that I study. But there's recommendations where we adjust the fertilizer rate. Often we talk about the parts per million nitrogen, and then the other nutrients are adjusted in proportion to that. And so at the early vegetative stage, during propagation, say we're at 100 to 125 parts per million nitrogen. During late flowering or late vegetative and into peak flowering, we'll be up to about 200 parts per million nitrogen. And then we will cut back down on that about 2 weeks before harvest. So that gives us a target EC of 1 to 1.5, up to 2 to 2.5 during the period when the plant is using the most fertilizer. So I want to mention briefly some of the in-house methods that we have. So if you buy a pH and EC meter for about $200 total, you could do either the pour-through or the 1 to 2 dilution method. Those are easy to do in-house, and then laboratories will usually use the saturated media extract method, which is a different method. So you can buy handheld pH and EC pens. They'll cost about $100 per meter. You want to use a reputable brand, some that I've had good luck with, not to exclude others, but our Blue Lab, Hanna Instruments, and Oakton. Some are dual purpose, so they can measure both pH and EC. Be sure to check the EC unit. There's some different units that are used. I like the ones that measure EC in decisiemens per meter instead of ppm. And then the pH meter needs to be calibrated every day that you use it. So you get a pH 4 and a pH 7 reference solution, and it'll take about a minute to calibrate it before you use it. So for the pour-through method, which is the kind of easiest non-destructive method, you're going to water your plants about an hour before taking the measurement so that they can get to container capacity. You're then going to place a plastic saucer under the container. And then depending on the size of the container, you're going to pour a known amount of distilled water on top. And then that's going to push out a leachate sample. So with a 6-inch pot, we're using about 50 milliliters of solution. And then you collect that leachate sample, and then that's what you're putting your pH and your EC pens into and analyzing. With the 1 to 2 dilution method, or if you send a sample to a lab for the saturated media extract method, you're taking slices or core of the media from where the roots are actively growing. So we find that salts can build up at the top surface as well as the bottom. And so we want to take samples of soil from the middle of the container where the roots are actively growing. You would take samples from 10 representative plants, pool those samples together. If you're going to send in a sample to a lab, talk to the lab, but they'll usually require 1 to 2 cups of material. And then if you're doing an in-house test for using the 1 to 2 dilution method, what you're going to do is air dry that sample overnight, combine 1 part by volume of the media. So often I like using little Dixie cups, little 3-ounce cups. So I'll take a 3-ounce scoop of that and then 2 cups of distilled water, mix thoroughly and let that stand for 30 minutes. And then you can use your pH and EC meter to test that water extract. This is also a really good method to use when testing a new potting mix. So if you don't have the pH and EC information from the manufacturer, you can test a new potting mix to make sure it's not too high in salts, like some of our compost-based mixes. And it can also tell you about the overall fertility. The saturated media extract would be a method that the laboratory uses. And I won't go into that too much, but then typically besides testing pH and EC, they're going to test the individual nutrients, the N, P, and K, and so on. And so it's nice to know what your mix is at the beginning. And then if you have questions about fertility over time, you can send a media sample into the lab. So this in-house monitoring for pH and EC really is most effective if you can do it weekly or at least every 2 weeks, and then graph that over time and track that over time. So here's an example I had of plants growing in containers with a peat perlite potting mix. We would sample them every 7 days or so. We started taking action when we got above a pH of 6.5, so we switched to a more acidic fertilizer for a week. We did that at day 28 and it was effective. We started getting out of range again about 20 days later, and we switched to an acidic fertilizer again for another week. So overall methodology for correcting for pH, if your pH is testing high, the quick method that you have is to do a one-time drench with acids, either 2 ounces of sulfuric acid or 3.5 ounces of phosphoric acid per 100 gallons of water. A lot of growers will use that through a fertilizer injector that's say a 1 to 100 injector. So then their stock solution would be 2 ounces of sulfuric per 1 gallon of stock solution, and then that gets diluted down to the injector to 100 gallons of water. Gradual methods to correct for a high pH are to switch to a more ammonium-based fertilizer, or if you know that your tap water source is high in alkalinity, is to continually add a dilute amount of acid to decrease your water alkalinity down to 80 parts per million calcium carbonate. Correcting for low pH, which is less of an issue here. I see it more in like Long Island, for example, where they have very pure water. We can use flowable lime or potassium bicarbonate. You do want to follow very carefully the label instructions because those, the flowable lime, if it's in contact with the foliage, can cause a burn to the leaf. And so you have to go back afterwards and mist any material off of leaves if it got on them. And you also want to flush your irrigation lines after using those materials. A more gradual method that we have is to switch to a more nitrate-based fertilizer. And then EC correction. So if we have a high EC, that means that we're either over-fertilizing or our water source or substrate is high in salts. So a quick method is to leach thoroughly with tap water and leach so that we get about a 50% leaching fraction. So about half of the water that you add to each pot is leaching out of the bottom, and do that twice. And that's gonna reduce the EC by about half. The longer term control would be to reduce your fertilizer concentration, leach more frequently with a 20% leaching fraction. So just do that periodically. And then test your water source to see if it's high in salts, or test your substrate source to see if they're high in salts to try to identify the cause. Correcting a low EC essentially is an indication that your fertilizer strength is not high enough. So you need to increase your fertilizer strength or reduce your leaching fraction if you are leaching at each irrigation event. With that, I just wanted to point out a few of the commercial testing labs. These will all do tissue, substrate, and water analysis. The cost tends to vary from about $30 to $45. And I find that growers typically, once they find a lab that works well for them, They tend to stick with that lab because every lab's results will be a little bit different, which is kind of funny, but they like, if you want to do an apples to apples comparison, you typically stick with a given lab after a certain point in time. Some of these labs, for example, I know for sure that J.R. Peters and Macro Micro Laboratory will do tissue hemp analysis, and they have sufficiency ranges that the laboratory can give you for what percent nitrogen should be in the leaves, for example, based on the stage that you're at. All right, with that, I will end, and we'll see if Larry gives us any time for questions.
Yeah, thanks very much, Neil. Unfortunately, we're going to try to get back on schedule. And in particular, Neil did not talk about all of his expertise in lighting. So if you have questions about lighting, also catch up with Neil. He is an encyclopedia of knowledge. So.
This has been a production of Cornell University, on the web at cornell.edu.